Hi guys, welcome back to AP Chemistry. This is Miss Gray and we're going to work on the ideal gas law. You saw this last year, but now we're going to learn some new ways to apply it. So hold on to your britches. Here we go. The ideal gas law, you already know, is we call this PIV-NERT, but let me show you basically where it comes from. Essentially, it's just this, that every time the pressure and volume were related to the number of moles and the temperature of the gas, it always turned out to be equal to the same number, R. So if pressure was 1 atmosphere and then temperature was 0 degrees Celsius, which is 273 kelvins, right, STP, the standard temperature and pressure, then for 1 mole, how much gas would we have? We learned last year we'd have 22.4 liters for every mole when we're under these standard conditions. So now get your calculator out and tell me what number do you get when you do 1 times 22.4 divided by 1 times 273 kelvins, or 273.15 to be precise. Remember this number? 0.082 when you have atmospheres and liters on top and moles and kelvins on the bottom. There's PIV-NERT. So there's our standard conditions. Let me move the writing out of the way. Where R represents the ideal gas constant because we keep getting that same number. Now here's more sig figs than what you learned last year. 0.0821 is technically 0.08206. That's probably what your calculator told you anyway, right? Because you all did that math when I told you to do it. Yes? No, you were waiting for me to do it? Shame on you. Do the math. Get your calculator out. The ideal gas law is used to describe the conditions of a gas as it is right now. The gas laws that you just used, Boyle's law, Charles' law, and so on, those are to describe when something changes. Like it says, what will the volume be? Or what will the temperature be? That's because something's changing, right? But if it says what is the temperature, then we would use PIV-NERT and not Boyle's law or Charles' law or the combined gas law in any form. So R, let's look at R, because there's more than one way to write this. We know 0.0821 goes with these units of liters and moles, atmospheres and kelvins. So I'm going to quite frequently be changing pressure into the units of atmospheres just because this one is easy to work with. But if you ever have energy in your problem, then you're going to have to use the form of R that has joules in it. So that would be the 8.314 joules per mole Kelvin. And that one's going to come up quite a lot too. Then if we had calories, of course, we would have to make an adjustment for R, or pascals, kilopascals, cubic meters, right? So we have all of these ways to express R. Generally, I just convert everything to liters, atmospheres, and kelvins so that I don't have to learn all of these. I just learned the first one. But the one with the joules, you're going to have to know that one too. That one's going to be printed on your AP exam. They give you like an equation sheet, so you'll have to know how to use it. All right, so if we're using the ideal gas, we're really talking about an ideal gas doesn't exist, right? It's a hypothetical substance that would completely follow the law, and not all gases work that way. There we go. So we know that the gases approach ideal behavior, but especially they follow this PIV-NERT very closely when the gas is at a low pressure or a high temperature, so they don't stick together very much. Even though most gases don't behave completely as an ideal gas, we use the laws anyway unless they tell us to do otherwise because they give us a good estimate. So let's do a few examples. I'm going to underline my important things. Here's my key terms. So volume is 47.3 liters, and then my number of moles is 1.62 moles. And it's heated until the pressure reaches 1.85 atmospheres. That's a lot of pressure. That's almost twice the pressure of the Earth's atmosphere. And we're supposed to find out what is the temperature. So let's use PivNert where R is equal to 0.0821. And now let's plug it in. If PV is equal to nRT, then how do we solve for the temperature? You guys are really good at algebra, but I'm going to show all the steps anyway. So divide by n and r so that T is isolated on one side of the equation. So we have PV divided by n times r. All right, now I'm going to put my numbers in. 1.85 atmospheres is my pressure. The volume is 47.3 liters. And we're going to divide that by the number of moles, 1.62 moles, and by R 0.0821, and I'm going to put in my units so that I know I can cancel everything that I need to cancel. Liters times atmospheres over moles times kelvins. It helps if I put all my units in. Okay, so now I have liters canceling, and atmospheres canceling, and moles canceling, and I'm left with 1 over kelvins in the denominator, which means I can flip it back up into the numerator. So what do I get? 657.9224373. And of course we know we don't need all of those numbers. Remember, this is in kelvins, so it's not quite such a ridiculously high number. It is big though, but we have a lot of pressure. So how many sig figs do we get to keep? Looks like I've got 3 sig figs in all of my measurements, so I better stop right there and call it 658 kelvins. Put a box around your answer because that's the way I like it. Let's work out another one. This time we're going to work with krypton gas. Volume is 18.5 liters. The pressure is 8.61 atmospheres. And then the temperature is 24.8 degrees Celsius. So let's change that right away to kelvins. So we'll call that 297.95 kelvins. And then R will use the 0.0821, and we are looking now for moles. Even though it's asking for the mass, mass is not featured in our PivNert equation, but I can use the moles to get to the mass. So let's find moles, as we normally do. When in doubt, go to moles. So I'm going to rearrange this equation so that N is by itself. Divide by R and T this time. So I get PV over RT will give me the number of moles. So let's put in our numbers. Pressure is 8.61 atmospheres. And then the volume is 18.5 liters. Divide by R, 0.0821 liters times atmospheres over moles Kelvin. And the temperature is in kelvins, 297.95 kelvins. All right, number of moles. Let's get there. Get your calculators ready. Okay, so I get 6.511609.273, that many moles. We're going to have to change this into grams though. So I'm going to need to use the molar mass. Changing moles to grams. 83.798 grams per mole. So that means 1 mole has a mass of 83.798 grams for krypton. So in my calculator, I'm going to take what I had and multiply it by 83.798 grams, and I get 545.6598. You know, we got all this calculator vomit. Let's round to, let's see, it looks like 3 sig figs again. So 546 grams of krypton, of course. There we go. So that's how we could get to the mass, even though mass is not in PivNert. We just use the moles and then go from moles to grams. You guys can do this. Let's look at another example. There's more. Okay, a sample of gas has a volume. Here's important stuff. Volume of 4.18 liters. at a temperature of 29 degrees Celsius. So let's change that right away to kelvins. Okay, and then the pressure is in torr, so let's change torrs to atmospheres. Remember how to do that? 1 atmosphere is equivalent to 760 torr, just like millimeters of mercury. So 732 divided by 760, that gives us 0.9632 atmospheres. Of course, I'm not going to round that figure until the very end. Now it's asking, what would its volume be at? So now we have a V1 and a V2. And we also have a T1 and a T2. So what would its volume be is what we're going to try and find out. At a temperature of 24.8 degrees Celsius, 297.95. And then we have a new pressure as well, 756 torr. So let's change that to atmospheres. Divide 756 by 760, and we get 0.994 atmospheres. Alright, so now I think we can simply apply the ideal gas law, right? Because that will allow us, no, not the ideal gas law, the combined gas law. That will allow us to calculate the volume, and it just says a sample of gas, so moles is not changing. So we're going to do P1 times P1 times V1 over T1 equals P2 times V2 over T2. And when we cross multiply to solve this proportion, and I'm trying to get V all by itself, then what do we end up with? I'm going to have some space up here. V2 is equal to T1 times P2. So multiply these. Oops, that's got to be on my denominator. So I'm going to have T2 and P1 and V1 on the top and P2 and T1 on the bottom. That ought to get us somewhere. Now the volume, the new volume, is going to be, gotta put in our numbers now, I don't want to mess this up here, 297.95 kelvins times P1, 0.9632 atmospheres, and then V1 is 4.18 liters. And then in the denominator we have, so P2 is 0.994, and then T1 is 302.15 kelvins. Now I do expect you to check me and make sure I'm doing this right, but here's the answer I get for V2. Look over here on the left, I got 3.992992131 liters. So I don't need all of those numbers, I just need 3 sig figs. No, this number has only 2 sig figs, so we better call this 4.0 liters. So we did not have a significant change in the volume, but because we had a slight adjustment in the temperature and the pressure, then that resulted in a slight change in the volume as well. Now let's look at how to use PivNert to solve for the density of your gas. Okay, well let's see, how do we find the density of a gas then? Density, we know, is mass divided by volume, right? So here's what I'm going to do with PivNert. Let's solve for volume. PV is equal to N times R times T. So to solve for the volume here, then I would take V is equal to N times R times T divided by the pressure. So far so good, right? I just solved for the volume. Now I'm going to substitute in the place of V in my density equation this piece here from the ideal gas law that is equivalent to the volume. So now density is equal to the mass divided by moles times R times temperature divided by the pressure. And of course, when we have a fraction and a fraction, we got to fix that, right? So this P kicks right back up to the top. Density is the mass times the pressure divided by the moles times the gas constant times the temperature. And that's how we find the density of a gas. But this right here is a handy key. When we take the grams divided by the moles, that, my friends, is the molar mass. So you don't have to really know all of the conditions of the gas. If you know its identity, then you know its molar mass, right? So you can find the density of the gas under any conditions when you already know its molar mass. That's pretty handy. So I'm going to rewrite this in this way, where I use this fancy M for the molar mass, okay, and that's multiplied by the pressure divided by the gas constant times the temperature. That will give you the density of your gas every time. So now that we've shown where that comes from, here it is for you to copy into your notes. Density is the pressure times the molar mass divided by the gas constant times the temperature. And so what we know is that the higher the pressure, the more dense the gas would be because it gets all squished together, right? And then if the molar mass is higher, then the gas will be more dense as well. So how do we determine the molar mass of a gas? Suppose that we just rearrange this. This is the same as this. It's just rearranged so that we've solved for the molar mass. So density, again, is mass over volume. If you can measure the mass of the gas and you can measure the volume that that gas is occupying, then you can determine its molar mass, which is handy when you're trying to identify a gas. Suppose you didn't know which gas it was, but we could determine at least its molar mass, and that would be a starting place. So we would take mass over volume and put it here. So let me write that equation for you as well. That would be the molar mass is equal to mass of your gas times R times T over the volume times the pressure. And that's it. So we have lots of ways to use the ideal gas law to get some interesting information. Here's an example of what we might do with density. What is the density of ammonia? Ammonia, remember, is NH3 at 23 degrees Celsius and 735 torr. You know, can I get a break here and just have atmospheres or kelvins? No, we gotta do both. Oh well, we can handle this. So density is the molar mass times the pressure over the gas constant times the temperature. And we know that the molar mass of ammonia is going to be 14 plus 3 is 17 grams per mole for ammonia. And what else do we know? The temperature is 23 degrees Celsius. So change that, add 273. So what do we get? 296 kelvins. And then the pressure is 735 torr. So let's change that to atmospheres so that I can use the R that I like. So 760 torr is equal to 1 atmosphere. That gives us a pressure of 0.9671 atmospheres. You don't need to write it all in, but I'll keep it in my calculator. And we'll use the 0.0821 liters times atmospheres over moles times kelvins. All right, then let's do this. Density of ammonia under these conditions would be 17 grams per mole times the pressure is 0.967 atmospheres divided by, let's see, what do we have on the bottom? 0.0821 liters times atmospheres over moles times kelvins divided by, or no, multiplied by kelvins, 296 kelvins. All right, I'm going to check the units and make sure that things are working out okay. Moles, atmospheres, and kelvins cancel, and I'm left with grams over liters, which makes sense for units of density. So now let's do the math. All right, and I get 0.676457, lots of numbers, grams per liter. Let's go ahead and change this to grams per liter. And how many sig figs? Looks like 2 sig figs will do. So we'll call this 0.68. Then I'm going to multiply it by 10 to the minus 3 so I can change liters to milliliters. And I'm going to have to move that over to get proper scientific notation. 6.8, right reduces, so I'm going to call that 10 to the minus 4 grams per milliliter. That's my density of ammonia under these conditions. Let's look at another example so we can see another application. The compound has an empirical formula of CHCl. So 1 carbon, 1 hydrogen, and 1 chlorine is the empirical formula. That's our mole ratio in simplest terms. So if we have a 256 milliliter flask at 100 degrees Celsius and 750 torr that contains 0.80 grams of the gaseous compound, then what is its molecular formula? So for us to be able to say the molecular formula, we need to find the molar mass of this gas. Okay, the empirical formula mass would be 12 plus 1 plus, what is chlorine, 35.45, I believe. That gives us 48.45 grams per mole for this formula. So if it turns out that the molecular mass is 48 something, then the empirical formula is the molecular formula. But if we have something that's more than that, we'd have to use a multiplier. So let's find out. All right, how does this go? The molar mass. Your P goes under the dirt. dRT over P. All right, well, let's give this a try. How do I find the density? Density is mass over volume. So I don't have to find the density yet. I just have to put mass over volume in the place of density. So I have mass over volume in the place of density. All right then, we are cruising. What's my mass? Oh, I have to do all these conversions. Blech. Oh dear. So let's see. Volume's okay, I can use that. 256 milliliters. That one's fine. But then the temperature, I'm going to have to convert, right? I'm not going to write that one down. 100 plus 273 is 373 kelvins. And then 750 torr, you're going to have to change the pressure. 750 torr. Change that to atmospheres. So I'm just going to put it, where does it go? Right here. Pressure. 0.98684, a whole bunch of stuff. And that's in atmospheres. And then the mass goes on top and the R goes on top. So 0.80 grams. And R, I'm going to squish it in here, 0.0821. And I'm going to write the units here. Liters, atmospheres over moles times kelvins. So let's see, moles is not going to cancel away, but atmospheres will, kelvins will. Liters does not. So let's change milliliters to liters. All right, so I move that decimal out in front. Now I have liters and I can get rid of that. Okay, looks like we're ready to do some math. And I'm getting a molar mass of 96.977921, blah, blah, blah. And I've got what's left? Grams over moles. Hey, that's the units for molar mass. We must have done something right. And it looks like this doesn't match, right? But it's about twice as much. So if you're not sure, take your molar mass and divide by your empirical formula mass just to see. And when I compare, here's what I did. Molar mass over empirical formula mass. Okay, well that's it for the ideal gas law. As you can see, it's a simple equation, Pivnert, but we're going to apply it in several different ways so that we can find out a lot of information about our gas just by knowing the conditions under which it's being contained.